Hi, let's learn about our next primitive, quadrilaterals. Now, quads also, just like triangles, they use the line. So if we know how to draw a line, we can then draw a quadrilateral. So quadrilateral literally means four lines, quadrilateral. So that's all that it is. And we draw them like this. Begin, shape, quads. Vertex, vertex, vertex. Like that, right? Put four vertices, and that defines our quad. 4 points, one quad, and we're good. And then, of course, we have to end our shape as well. End shape. Just like that. So a quad is basically any four-sided shape. That's a quad. Whoa. Let's try that again. That's a quad. Okay. Any four-sided shape made of four vertices is a quad. Cool. So the first thing to note about quad is that they do have winding, just like a triangle. Okay, so if I label these vertices V1, V2, V3, V4, then the winding goes, the edge vectors will be like this, and then the winding will be in that direction. So just like with your triangles, edge order, vertex order, sorry, is important. And just like with the triangles, we can use the cross product of adjacent vertices to determine the winding. All right. Unfortunately, however, it doesn't work out to be as clean or as simple as triangles. However, not as simple. Just because there's more vertices, there's more possible cases. There's more variety. Okay. There we go, come on. Having scrolling problems. So first of all, unlike triangles, quads can be convex, right? Triangles are all convex, but quads don't have to be. So they can be convex, just like our example there. That's a convex quad, right? It's all pointing outwards. But they can also be concave. Okay, and I'll talk about that in a second, but first I want to mention that convex or concave, these are called simple quadrilaterals. And we'll learn about non-simple ones shortly. So here's an example. I'm going to draw a concave quadrilateral. Let's try that. Right, bam, like this. That's a concave quadrilateral. And you could imagine E1 goes that way, E2 goes that way, not vertex, edge vector 3 goes that way, and edge vector 4 goes that way. So if I look at the cross products of these to see what happens, let's figure it out. Edge 1 cross product edge 2. Edge 1 turns left, it goes counterclockwise, so that's going to be bigger than 0. Edge 2 cross product edge 3, 2, it turns left, it goes counterclockwise. Good, we're bigger than 0. Edge vertex 3 goes to 4. What happens here? Edge vertex 3 cross product edge vertex 4, it turns right, it goes clockwise, so this one's going to be less than 0. And then edge vertex 4 cross product edge vertex 1 turns left again, turns counterclockwise again. That's right. Okay, so this was clockwise, the other ones are counterclockwise. Okay, I want to highlight this. So in a concave triangle, one of your cross products will have the opposite sign, right? So this was a counterclockwise winding quadrilateral. One of the cross products goes the other way. If I had a clockwise winding, the same thing, one of them would have been counterclockwise. We can also say that the majority sign determines winding. So here, even though one goes clockwise, because the others go counterclockwise, we call it a counterclockwise quadrilateral. Okay, so that's a concave one, and a concave one will have one cross product in the opposite direction, whereas you won't have that with a convex. It'll be like a triangle. They'll all give you the cross product with the same sign. We also have complex quadrilaterals. Let me draw one for you. So V1 goes to V2, goes to V3, goes to V4, and goes back. So this is complex. There's a cross here. It self-intersects, okay? So it makes that a complex one. Let's do the same exercise. This is my edge 1. This is my edge 2. Edge 3, they go like this. And then edge 4 goes that way. So if I do edge 1, cross product, edge 2, it goes counterclockwise, so it's bigger than 0. Is that right? That's right. Edge 2, cross product, edge 3, it turns right now, so this is less than 0. It goes clockwise. Edge 3, cross product, edge 4 turns right again, so this is clockwise. And then edge 4, cross product, edge 1 goes counterclockwise. Okay, so now we have a different situation. We have counterclockwise, counterclockwise, we have clockwise, we have clockwise. All right, so you have both a balance. We don't have a majority rule of counterclockwise or clockwise. So with a complex quadrilateral, we say there's no defined winding. So there's no defined winding for that one. We have another case. I should probably highlight these. Convex, concave, complex. There's another case I want to talk about, just like with the triangles. We do have degenerates. We have degenerate ones. And that's where they're basically not a quadrilateral at all. And so I could imagine degenerates, you could see something like this, right? One, how's it go? 1, 2, 3, 4, something like that. I don't know. And in those cases, some or all of your cross product will give you 0. 0 is collinear or coincident, right? So you're going to have those cross product problems. Let's take a look at my slides real quick. Let's bring those up. Slide 9. Okay. So here, the problems are always not always that obvious with your quads. Okay, so you can have this is a quad turned into a triangle, and we get a cross product here between 3 and 4 because they're collinear, and they get a cross product of 0. But this isn't degenerate in the sense that it has no area, right? But it isn't a quad. And then over here we have the degenerate case where you could imagine you have a bunch of zeros, but not all of them are 0. These are 0, these are 0, but the other ones we have a turn, but it's actually no area. So it's not that simple. Okay, and you'll see me come back to this in a moment, but quads are not quads are a little more complicated to determine, and it's not as simple as having a few rules under your belt with the cross product and knowing exactly what's happening with that quad. This was slide 9. I'm also going to give a demo now. Demo sketch 3. Okay, so let's bring that up. And there we go. Okay, so let's take a quick look at this. I'm only going to show that I begin quads, and I'm going to draw a bunch of them with 4 vertices each. I'm going to print out at the bottom convex or concave or whatever, so you can see which ones we're printing. So let's look at these. So this is a standard convex quad, and as you can see, it's drawn correctly and filled correctly. So that's nice. Here's a concave one, bam, bam, and it goes in, okay, but it drew okay. Okay, so it drew this concave okay. Here's another concave, but it didn't draw okay. Look at the fill. It filled it in as if it was convex. Here's a complex one, and it drew it wrong. Here's another complex one. The ordering changed, and it drew it wrong in a different way. So depending on the ordering of the vertices, you get a different result. And here's a degenerate one that looks like a triangle, but still okay. And here's another degenerate where it's not okay. It filled it in when it wasn't supposed to be. And here's the line, which because we have the stroke turned on, we still see the line, but you'd get nothing in this case if you drew it with just the quad. So we have all these cases, and many of you are probably starting to get confused. Convex worked, concave kind of worked, but not really. Degenerates are kind of random. So what do we do with all this? Well, it turns out that only convex quads are guaranteed to draw correctly. We're not stupid. We know how to do the math. We can figure out how to draw all of these correctly. It's slow and expensive. So what happens in graphics instead is that more and more they assume the game designer or the graphic designer, your job is just to use convex quads, and if you're going to use concave, don't bother because they might not draw correctly. What's even more frustrating is if you went and wrote this in, say, Java OpenGL, you'd get a different result. It depends on what flags are set. Your OpenGL version changes, you get a different result again. The rule is, if you're going to use quads, stick to convex. If you have a concave, you got to fix it. You got to break it up into triangles, or a degenerate, you got to break it into triangles. And there are algorithms for this. We'll learn some of that later, but this whole triangulation of meshes is a really popular problem in computer graphics. So, from that demo, what did we learn? In bright red, only convex quads are guaranteed to draw correctly. Okay. Basically because of speed. Graphics libraries make this assumption. For optimization. A bit more work on the front end or processing your data before it hits the graphics card makes the graphics card faster. Part of this is it uses the cross product sign, and as we saw above, it gets messy if you're away from convex. If you're with convex, they're all the same. It makes that assumption. We're good to go. Okay, and in fact, modern OpenGL no longer supports quads directly. Right? Your job to fix it. Okay, so let's stop here, and then we'll come back now that we've done quads, and we'll finish up this unit with polygons.